In this video, I want to talk about retrieval augmented generation. And retrieval augmented generation is this idea that our large language model might not have the context it needs to answer a user's question. And the way we insert that context is we perform a search and we find the relevant parts of documents that can be used to answer that question. So how this happens in practice is, let's say we have a bunch of documents, we split them into parts and we call these parts chunks. And then we embed these chunks, put them in a vector database, and when a user has a query, we find the most relevant chunks. And then instead of passing the large language model just the query, we also append the relevant chunks to the query and then pass that to the large language model. So let's actually do this in practice, see how this is done. Here we're going to install some libraries. The first library we're going to install is LlamaIndex. And LlamaIndex is what we're going to use to actually turn those documents and split them into individual chunks. Next, we have FastEmbed. That's going to generate our embeddings. OpenAI is going to be the thing that takes our query and our chunks and returns a response with a large language model. And of course, we have a KDB.AI client, which is going to be our vector database. So I already have this installed. Let's import some dependencies. And I also have my environmental variable set, so I'm going to skip this step. But notice that I have OpenAI API key because we are making an external API call to OpenAI. And let's also install, let's also fetch our dataset, right? So we're fetching a Paul essay dataset here, which is a bunch of essays by Paul Graham. And this is going to take a second. Now we have a bunch of essays by Paul Graham. Now let's create a KDB.AI session. And let's define the table schema. Now the table schema is going to have two columns. It's going to have a text column and it's going to have an embedding column. Now, our index is going to be a flat index. In this case, it doesn't really matter which index we use, right? Because the amount of data that we have is so small. Flat index, typically in search speeds are faster. HNS-W index, for example, our query speeds are going to be much faster. So here we've already created a table. Let's run this again just in case. Now, let's also define a node parser. So we're going to define a sentence splitter. And what this does, it's a LlamaIndex tool to take your individual documents and turn them into chunks. So it's going to take a document, say, split it into 5 chunks. So we're using LlamaIndex to load our documents and output chunks around the size of 500 characters. Now it's a sentence splitter, so it's going to try to keep sentence boundaries, and it's going to have a chunk overlap. And overlap allows us in practice to get better results with retrieval, because we want to pass as much relevant context to the large language model. And by assigning an overlap, we could say, hey, like this chunk might be closer than that chunk with that overlap, instead of just trying to get sequential chunks. Now let's define our embedding model and then embed all our documents. Now, one thing to note is that when I generate embeddings from my data set, I usually try to do this locally, not with external APIs. For example, OpenAI has an endpoint where you could generate OpenAI embeddings. But if you use OpenAI embeddings, those are closed source embeddings. When you're doing inference, when you have a query and you're turning that into our vector so you can search your vector database, you're going to have to use the same embedding model. And that means you have to depend on OpenAI's latency constraints. If they decide to send you a really slow response, and on average the responses are actually really slow for their embedding API, then you're just stuck with that. So you're doing an external request from your server, and that's fundamentally slow as well. So if you use local embeddings, you can generate those embeddings extremely quickly. And that means faster response times when you're doing RAG for your users. Now, is this section of the latency trivial compared to the actual large language model response time? Well, maybe a little, but let's say your time to first token in practice is 300 milliseconds. Well, do you really want to add another 100, 200 milliseconds on top of that? I'd say no. I try to use open source local embeddings for my entire pipeline. So now let's print the first document. And, the first chunk, right? This is in the first document. This is the first chunk. Well, technically the second chunk. And Yeah, it looks good. So let's create a data frame with our text and our embeddings. And let's look at it. So it should have two columns, text and embeddings. And that's exactly what we got. Every text chunk is around 500 characters. And then we have some embeddings, right? Looks great. Let's insert into our table. And now let's actually perform RAG. So what we're going to do here, we have a query. And let's generate a query embedding. Nice. Now we can do a search. So we're going to do a search using our index. And we're going to get 10 results. Now let's look at this search result. We have our sentence similarity. We have our text. We have our embedding. We only got the top two results, but we returned 10. And then, sorry. Now we're only showing the top two results, but we return 10. So we're going to pass 10 to our large language model. Now our RAG function is very simple. What it does is we have our retrieve data in our prompt. And then we have this additional command of answer the following query in 3 sentences based on the context, and only the context. And then for every single chunk that we've retrieved, we're going to append that to the prompt. And then we call the large language model and ask it to answer that full prompt with that added context. So now let's create this utility function to just help us visualize the response. Now let's run this RAG function. So for this query, how does Paul Graham decide what to work on? We get this answer, and this answer is based on the essays, right? This isn't based on the large language model's internal understanding of Paul Graham's essays. And that's it. That's all we have to do to perform RAG. This RAG function is extremely simple, and you can actually implement this in like 3 or 4 lines of code if you'd like. So, yeah, that's it. I hope this was helpful. This is actually the last video in a course on using KDB.AI and vector retrieval in general. So I really hope you've enjoyed this course. I put a lot of effort into making it. And if you'd like to see more content like this, follow me on LinkedIn. Make sure to check out KDB.AI if you haven't yet. And I hope you have a great journey experimenting with retrieval and large language models in the AI space in general.